Und wir legen gleich los mit dem nächsten Vortrag. Der Titel ist Building Function Classification, the Tooling of Social Media and Remote Sensing. Und die Vortragende ist Chang Bai von der Technischen Universität München. Sie ist Master in Computerlinguistik und Informatik an der LMI München. Sie arbeitet im Bereich Natural Language Processing in Projekten mit der Deutschen Börse und Lufthansa-Technik. Derzeit ist sie Doktorandin im zweiten Jahr am Lehrstuhl Data Science of Earth Observation an der TU München und ihre Forschungsinteressen sind Analyse von Social Media Daten, Large Language Models und Natural Language Processing Anwendungsfällen. Und der Vortrag wird in Englisch sein. Yeah, the floor is yours.
Vielen Dank für die Vorstellung. Aber mein Vortrag will auf Englisch machen. Ich hoffe, das ist okay für alle Ihnen. Hi everyone, I'm Shanshan Bai, and I'm really happy to be here today, not only because I can introduce my work to more people, but more importantly, I think my background is kind of different as most of you here. In the past, I work mostly with the text data, and I help companies to solve NLP-related use cases. And for the topic I want to talk about today is that I'm trying to use the text data from social media to improve a classical use case in Earth observation, which is to predict the functionality of the building. And I'm trying to use text data to, in addition to the remote sensing image. And here's the agenda of my talk today. I will first introduce a bit about who is interested in knowing the functionality of the building. And then I will introduce how we collect the data, how we label the data. And this is the major part of the work. And also, I will bring out our core research question and how we did the experiment, how is the results, and in the end, our finding and how to improve our work in the future. So who is interested in knowing functionality of a building? I think not only the urban organizers, they can use this information to build a smarter city, and also people who are working on the natural disasters can also use this information to better reallocate the resources. And also some insurance companies might be interested in knowing this because they can use this information to build a better predictive model for their insured building. And I will jump right into how we collected the data set. So like a lot of work of UDAM, I'm also using the OpenStreetMap to get the metadata of the buildings. So two information we're using from OSM is that the building coordinates, so we know where exactly the building is. And the next one is the building tag from OpenStreetMap. And since we find out that building tags on OpenStreetMap can be really various, can be really incompleted, and therefore we have mapping this finer text into three major categories, which is commercial building, residential building, and other type of building. And then since we know where a building is, we can get the image of the building. This is what the classical way we do. We are relying on, in the past, we are mostly relying on the remote sensing image. So this image tells us the color of the building, the shape of the building, this kind of morphological or physical appearance of the building. But the problem is sometimes in the really dense urban area, buildings can be very similar to each other and lack of more details information. And since we are trying to do a building level classification, we need really fine granularities of information. That's the reason why we introduce another type of data source to this task, which is the GEO.KI twits data. And that means we have to first collect the data for a few years. And among them, not all has the GEO.KI. And we have to pick out the ones with GEO.KI and then assigning these twits to the closest building. And here we have this heuristic rule. As long as the twits was centered in the 50 meters in the radius of a building, then we assume this twit was sending from this specific location. So in this way, all our twits also have the same label as the building. So eventually, actually, my colleague has built this data set. He spent years in this work, even though I just only wrote 2 sentences here, but this is actually the most difficult part of this work. We have eventually collected 2.7 billion twits in 43 different languages. So this is a very large-scale multilingual data set. And also the building is covered 42 different cities all over the world, and in total 7 million buildings. So this is a really large-scale data set, and we are going to publish this data set. And and hopefully we can also promote other researchers to do this research further. And here's the visualization of how our data looks like. So we have each building has a unique image here. And also, besides that, there might be multiple twits sending from this building. So at least one twit, but it could be more than one twit. And they could be multilingual. And so this converts this social media data into a text classification task. And one way doing is that we just use the individual independent twits and predict the label of each twit. But there's another way is that we can just concatenate all the twits that's standing from this building into a long string. And then actually this also solves the imbalance issue of 2 different modalities. Now we have only one long string and one image. So we have the data now, and we want to ask this core question of our research: how much can twist text data contribute to this building function classification task? To answer this question, of course, we first try out only using the classical way, relying on the remote sensing image for this task. And here I choose the 2 different vision model. So VIT is a really generic vision model, nothing special about it. And DOFA is a domain-specific foundation model, actually also mentioned yesterday. And the difference is that DOFA supposed to have more domain-specific knowledge since it was pre-trained on a lot of remote sensing data. But after running the training, we find out 2 different models didn't make a big difference. Therefore, we try out also using text data only for this task. And likewise, we also choose 2 different language models. And the first one is the multilingual version of BERT, which is usually a default choice if you are analyzing multilingual text data. And the second model is Llama 3, which is the latest open source large language model. The reason we choose it is also because it's multilingual large language model. And the reason we want to compare this to different models is that usually for classification tasks, we would just choose the BERT model. But Llama 3 was not originally designed for classification problem. It's actually a generative language model to generate the text like ChatGPT. But here we are just curious if this embeddings from this larger model might bring out better results. But eventually we find out the model complexity or model size didn't make a big change here. Of course, eventually we fused these two different modalities. We also try out two different ways to fuse these two modalities. The first way is that we simply trained two independent classifiers. And in the end, we just average their result. So this is very straightforward and intuitive way. And the second way is that we already fused the embedding from these two encoders before feeding into the classifier. And eventually, the second way that feature level fusion is performing better than the first one. So based on the result, our finding is that we find out that raising the complexity or the scale of the model is definitely not the key for this task. And we also think that fusion twist data into this task definitely is better than just using one single data source. And we also find out that if we concatenated all the tweets from a building, it will also have the better performance, just classifies them independently. But we also, of course, notice that image is still being really dominant for this task. And text data actually only brings very limited contribution at this stage. This is because the data set is still too noisy. Actually, I need to come back to the way that we collected the data set. So although we use this so-called weak supervision way to get the data and label the data, we get the data easily and fast, but this also get a lot of noise. For example, yesterday there was a presentation about how inaccurate and incomplete of the building attributes on OpenStreetMap. And of course, this will also lead us, this task, to have some label noise. And besides that, there's another more critical issue or critical type of noise in this data set. So usually when we are using social media text data, we would face the first kind of noise, which is sometimes called linguistic noise. That means there will be misspelling, typos, or random URLs or abbreviations in the text. But I wouldn't have too much concern on this type of noise because since we are now using deep learning models, and also the modern language model is already proven kind of robust to this kind of noise. And what makes me more concerned is about the second type of label noise that introduced because of the inaccurate OSM data building attributes, but also sometimes people sending tweets, the content is not definitely about where they are. For example, maybe we are sitting at home and posting something about a restaurant, and that makes this kind of A/B location mismatch. But what interests me mostly is the last kind of noise, and I name it as a content noise, which means the way we collected this data set, we have this heuristic rule that as long as the tweets was standing in the area of the building, then we consider it's tweets standing from the building. But actually, people talk about everything on internet. Maybe the content is completely irrelevant to the building. For example, if we just send a really generic tweets like, this is really nice weather, and this kind of information wouldn't really be so helpful for this task. So this is exactly what I'm going to do next. And hopefully I can use some uncertainty method to find or filter this completely irrelevant noise before training, and hopefully this can raise the accuracy of this task. And I believe most of you, since we are having different background, maybe you are looking at this problem from a completely different perspective. And any questions are welcome if anything is unclear. Thank you.